Okay, welcome to this video for Chem 161, Chapter 4 Materials. We'll be looking at Lewis dot structures for atoms and molecules. We turn to Lewis dot structures to help us not only reflect the population of valence electrons around an atom center, but we also use this to help us predict how many covalent bonds might occur when we have covalent bonding, and therefore how many shared electrons need to be established to give us the bonds for the architecture of the molecule. So we'll start with the idea of what a Lewis dot structure is for an atom. Okay, and so what we're going to do is we're going to use a chemical symbol to represent the element in question. And not only that, that symbol will also include the core electrons that we've identified from electronic configurations. Okay, so when we look at something like the electronic configuration for example, carbon, we know that the electron configuration for carbon is 1s2, 2s2, 2p2, and we know the shorthand for this is carbon, helium, 2s2, 2p2. All right, so with that, when we establish the Lewis dot structure for this atom of carbon, what we do is simply list the carbon symbol. Just by listing capital C for carbon, we've included the element identity and the core just by writing the letter C. Now the 2p2, 2s2, those valence electrons need to be populated around the feature with fourfold sort of positioning. Okay, so we kind of put them top and bottom, left and right. And so the valence dot structure for carbon would be this, or better said yet, this is the Lewis dot structure for carbon. Okay, for something like oxygen, we have helium again, 2s2, 2p4. And so we see that there are 6 electrons needed. So the Lewis dot structure for oxygen is going to show 6 dots. Okay, so we'll start 1, 2, 3, 4. I've put 4 around this. At this point, I need to start pairing up electrons, so 5 and 6. We've now listed all 6 valence electrons for oxygen. I have 2 unpaired electrons on that oxygen center, so this is helping me understand that I need to do sharing at each of those sites to help provide some covalent bonding and some electron sharing to make this oxygen look like a full octet. Okay, so again, we've used dots around the symbol, which represents the element and its core, and these dots represent the valence electrons. Okay, so pause the video, make sure you can do some of these if you want. In principle, you should be able to predict the Lewis dot structure for any atom from the periodic table. Of course, avoiding the homonuclear diatomic elements because, of course, we know those automatically share electrons as well. Okay, so with that skill behind us, we're now able to apply this method to actually build up the structure of covalent compounds. And we'll see that this structure is more of a two-dimensional representation of a molecule, and later we'll evolve this into a three-dimensional structure. So that is the power here, is that it ultimately lends to a tool that will allow us to predict the three-dimensional structure and things like polarity. So a Lewis dot structure, again, is used for covalent compounds. It builds off ideas that we have for the atoms as well. And we're going to use valence electrons to establish sharing of those electrons to get octets. Okay. What we'll see in these Lewis dot structures is that a solid line will represent a bond, and a solid line is going to be a pair of electrons. So 2 electrons is in a line in a Lewis dot structure. And of course, those are shared electrons. Dots will also be found in these structures, and dots will represent unshared electrons. And we'll see if there's two dots like we have here already up in oxygen, we'll call that a lone pair. All right. Okay. So if we're to try to start drawing some Lewis structures, we're going to need some rules. Okay. So if we were to begin with something like CCl4, we'll start with our steps for drawing a Lewis structure for this over here. So the first step says determine the total number of valence electrons for the compound. Okay, so we've done carbon already. We see that we have that in the CCl4. So we make a little bit of a chart here. Carbon, and we're going to get valence electrons from chlorine. We have one carbon in this structure, and we need to know how many valence electrons. So I'm going to populate this blank area here with the valence electrons. We see from the shorthand notation for carbon, as we saw earlier, that we have 4 valence electrons. Okay, so I'm going to put a 4 here. All right, with chlorine, I have 4 chlorine, so I'm going to put a multiplier of 4 on that and determine the number of valence electrons for chlorine. Okay, so we'll just make some room for that. Using our periodic table, we can see that the shorthand notation for chlorine is going to be neon. Right, so we start here at neon, we advance to 3s2, 3p5. Okay, so this tells us that we have 7 valence electrons. VE, sometimes abbreviated. And so we're going to put a 7 in that blank spot. Okay, so the total here is going to be 4, and we're going to have 28. So the total valence structure has to have 32 electrons associated with it. We've just determined the total number of valence electrons for the example molecule, that is CCl4. All right, step 1 complete. Step 2, we need to draw the skeleton. Okay, so a skeleton is going to have the elements in question, and we're going to show connectivity. We're going to use some of the valence electrons, some of the 32 in our case here, to show that connectivity. Every time we draw a line, that's a tether between atoms, that represents 2 electrons used from the 32 in this case. Okay, so to help us with this, we have some guiding principles. So usually carbon goes in the middle. Okay, so that's a good place to start. And also, if you don't have a carbon, you have a justified approach in putting the least electronegative element in the center of the structure. Okay, so recall your ideas about electronegativity from previous studies. CCl4, well, we see that chlorine is more electronegative than carbon, and also we're given carbon, so we're going to put carbon in the middle of this structure. Now, ideas above for the positioning of electron groups are kind of fourfold around this structure, so we're going to do the same thing. We're going to use that fourfold architecture to help us, and we'll see that as valid in all Lewis dot structures for molecules. So work with sort of north, south, east, and west positions for groups around this. To build the rest of the structure, I need to tether those 4 other chlorines. So I'm going to use lines. These, at this point, are 2 electron bonds, and I'm going to position those other chlorines around the structure. Okay, my Lewis dot structure is now reflective of the stoichiometry and the formula. 4 chlorines, 1 carbon, we're good there. We've built our skeleton. We need to take stock of what we used. Okay, so at this point, we have used some electrons. Each line here represents 2 electrons. So we've just used 8 electrons. So we're going to modify our total here to show that. Okay, so we've got 24 electrons remaining after having built our skeleton. Okay, so with that, now we need to distribute pairs of electrons around the outer atoms to satisfy octets. So we notice that chlorine here does want to, in fact, have an octet. The only exception would be something like hydrogen, which would want a duet, and we don't have hydrogen in our structure. So we simply want to satisfy octets and position those pairs of electrons around each chlorine. Okay, so we'll start at any chlorine position and just sort of count. 1, 2, 3, 4, 5, 6. I've just used 6. I've established 8 electrons around this chlorine. An octet is there. 6 electrons used. 7, 8, 9, 10, 11, 12. Establish an octet around this chlorine. Recall that we've got 2 for the line bonds, so that's how we're satisfying the octet. That shared pair of electrons that's in the line that was used for the skeleton counts as 2, and we have 6 other electrons at each of these carbons so far, 3 lone pairs at each of these chlorines so far. Used 12 so far. There's another 6 that have been used. We have an octet at this center that's using 18, and another 6 for the apex chlorine here. That's another octet. Okay, so each of these chlorines has an octet, and we've just used 24 valence electrons for that. We have no more valence electrons to apply. So as far as populating valence electrons onto our structure, we are done at that point. We can move on. So if there are valence electrons that remain, so if our answer here was not 0, we would apply the next rule. It says to apply those extra electrons on the central element. Okay, we don't have to do that, so we can advance past this. Okay, at this point we do have to look carefully at rule number 5. Check if the central atom has an octet. So we look at that carbon carefully. How many electrons are around it? We have 4 lines. Each of those lines counts as 2 electrons. So we have 8 electrons around that central carbon. That is an octet. Okay. If that weren't the case, we would consider borrowing a pair of electrons from a neighboring element to establish multiple bonding. We'll show that in the last example on screen here. Okay. And then lastly, if we were handling polyatomic ions, we would use brackets around the whole structure to reflect the overall charge. And we would consider perhaps if there were more than one correct answer after doing things like borrowing pairs, if there is a better choice based on some formal charge calculations that we'll do in a later video. So we'll hang on to rule 7 for a later moment when we understand how to calculate formal charge. Okay, so at this point, this Lewis dot structure is correct. We've used all valence electrons. We have none left. We have octets all the way around. And this is our correct Lewis dot structure for CCl4, carbon tetrachloride. Okay, good. So let's try another example. We'll use NH3 as the next example. So I'll just make some room for that. Okay, so this might be an opportunity for you to pause the video and try this one before resuming the video. And again, we're working on NH3 here, and we know that nitrogen is in the center. Okay, so NH3. Okay. All right. So our first rule is to determine the total number of valence electrons in the structure. Well, if we start with nitrogen, nitrogen is in the 5th column. So we're going to see 5 valence electrons come for that. 1 nitrogen, 5 valence electrons. Okay, that would be a 2s2, 2p3, 5 valence electrons there. We have hydrogen. There are 3 of them. So a multiplier of 3 on that. Hydrogen's right here, only a valence electron count of 1s1. So we get 1 electron as a valence electron from each of the hydrogens. And we now have our total. So 5 and 3. The total here is 8. We have 8 valence electrons to work with in this structure. Good. Step 1 complete. On to step 2. Draw the skeleton, and we're told here nitrogen in the middle. Okay, so we'll start with nitrogen in the middle. I now have to populate 3 hydrogens around that. So we'll work with the ideas of north, south, east, and west. Okay, so no kind of wrong way to do this. I'm going to leave the top spot empty. You could have left the left or right or bottom spot empty instead. It's all fine. Okay, there's 3 tethers for the 3 hydrogens, and here they are now. We've just used 2, 4, 6 valence electrons to establish our skeleton. So -6. I have 2 valence electrons left. And we'll move down down the rules. So it tells us to distribute pairs of valence electrons around outer atoms to satisfy octets, and note that hydrogen only gets 2 electrons. So each of these hydrogens already has a duet, given that there's 2 in the covalent bond that is shared between nitrogen and hydrogen. We've already established its duet. No more valence electrons go on to the hydrogen. So we do not need to apply rule 3. We're on to rule 4. If valence electrons remain, add lone pairs to the central atom. Okay, so a central atom is nitrogen. We have 2 left to use. We're going to put a lone pair here on that nitrogen. That would be -2. We are now done. And we've established all valence electrons into our Lewis structure at this point. Now we have to check if the central atom has an octet, rule 5. If not, take electrons from pairs surrounding the atoms. Okay, so looking at nitrogen, I see 2, 4, 6 electrons in the covalent bonds, and an additional 2 as a lone pair at the top position. So that's 6 plus the 2, that's 8. We do have an octet at that central nitrogen. So we are good there. And we don't have a polyatomic ion. And at this point, we don't have information on formal charge, but we'll do that soon. And this is as correct as we can go at this point, and is in fact the correct Lewis structure. NH3 has 3 hydrogens tethered with a 2 electron shared bond as a single bond, and a lone pair at the top position here. Okay, very good. So let's do one more together, and we'll see how we get to apply the rule of borrowing from an outer electron in doing that. Okay. Okay, so again, this might be a moment where you pause the video and resume once you've had a chance to try this more complicated example and test your answer. Okay, so we have to determine the total number of valence electrons to work with. Carbon in the 4th row, so we have 1 carbon times the 4 valence electrons we're going to get from that. Again, 2s2, 2p2 for carbon, 4 valence electrons. Oxygen, this is in the 6th column. We'll have 1 of those, 6 valence electrons because it's in the 6th column. Again, 2s2, 2p4. We have chlorines to handle. We have 2 of those, so 2 times, and now we got chlorine. That's in the 7th column of the periodic table, so we're going to get 7 valence electrons there. So our totals here are 4, 6, and 14, and so we have a total here of 24 valence electrons to work with. Number 1 is done. Build our skeleton. Least electronegative element goes in the middle. Well, that is in fact carbon, and we've also said that carbon typically goes in the middle, so we're good there. Carbon in the middle. We now have 3 additional atoms to link to this, and we'll use single dashes to show that linkage. Okay, so we'll put maybe the oxygen here at right, chlorine down below, chlorine down below. Again, thinking about north, south, east, and west only. There's our 3 spots, and the top position is empty at this point. In doing so, we've just used 6 valence electrons, so I'm going to keep track of my total. I now have 18 valence electrons to work with for the remainder of the exercise. It now says to distribute pairs of electrons around the outer atoms to try to satisfy octets there. So typically at this point, we might have to choose between oxygen and chlorine. So we'll start with the more electronegative option, and that's going to be the chlorine. So we'll start there, 2, 4, 6, an octet of chlorine, good for us there. We've just used 6 valence electrons from the 18, 2, 4, 6. So we've just used a total of 12 at this point from the 18, and we have another 6 to go, 2, 4, 6, and there we go. There's the final 18, minus 18, and we now have 0 valence electrons left. We've populated this Lewis structure with the correct number of valence electrons, and we've done so by putting them at the outer atoms. No valence electrons remain, so nothing to apply on the carbon. Okay, and then we're on step 5. Check if the central atom has an octet. Carbon at this point has 2, 4, 6, only 6 electrons around it from those single bonds, from those shared pairs of electrons to each of the tethered atoms. We only have 6. We do not have an octet at this central carbon. So we have to borrow a pair of electrons. So you'll see that the correct choice here is to borrow a pair of electrons from oxygen. And so we can kind of show that idea here. It's like I'm pushing those 2 electrons into the vicinity of that single bond to establish a double bond. And this is going to give us the correct answer. Okay, so after we do that, what happens is we need to establish a new bond in that position. So we're going to remove that lone pair and instead put 2 more electrons in here as a double bond. Okay, so there that is. Notice that we're missing that top lone pair at this point. By doing this, by borrowing a pair of electrons, we've now put an extra pair of electrons near carbon. Carbon now has 2, 4, 6, 8 from the double bond. We now have an octet near that carbon. You might be wondering what happened to the oxygen. It sort of lost a lone pair. Well, do we still have an octet at that oxygen? 2 lone pairs, 1, 2, and a double bond with 4 electrons in here. So we have, in fact, an octet at that oxygen as well. Okay, so this is the correct move to help us get that satisfied octet at that central carbon. Okay, and this is the correct Lewis structure. We'll rationalize in a later video why borrowing from chlorine was wrong, and the answer will come from assigning formal charge values to each of these centers and comparing with other Lewis structures where we would have double bonds elsewhere. And we'll show that the formal charges at each of the positions here are 0, and that is in fact what we wish. So this is the correct Lewis structure for C.